Hello friends, this is Mowgli for the ARM based development course. So in this sixth session, the topic that we are going to cover, we are going to start the instruction set of ARM now. So this is going to be at least 5 to 6 sessions. We will go into details of all kinds of different instructions that ARM support, and then we will see how to use them later on. But during the learning of instructions, I will give you some sample code also, so that you understand how each instruction functions. And I expect you to try the ARM simulator, writing these instructions in that and write out what happened, so that you understand when you play with the simulator, you understand the instructions better. So in today's discussion, we will be touching upon data processing with class of instructions. Before that, I will touch upon the conditional execution, which is a very unique feature of ARM, and then we will go on from there. There will be another follow-up section. We will talk about other instructions of ARM. So with this, we have completed the unit 2 also. Now we are entering the unit 3 of this course. So the topics that we are going to cover, I will just give you how the ISA, the instruction set architecture, and the processor variants are mapped. Okay. Then at a high level, what are the different types of instructions, and then we will go into the instruction set of ARM7 TDMI, which follows the ARM v4t ISA. If you remember, a processor will be based on some instruction set architecture. So there could be different families of processors following a particular ISA. So they will have, what are the differences among them? Though they are implementing the same instruction set, they might have different features or hardware modules to enhance the execution of those. And in the instruction set thing, we will be talking about conditional execution and data processing instructions to start with. So this is a nomenclature which I introduced earlier. So ARM family has this kind of acronyms used for indicating different features, different hardware modules which are supported in a particular processor. So when you hear ARM7 TDMI, if you know that this is a 7, S is 7, so it's a ARM7 family of processor. T, it has a thumb mode, which is a 16-bit wide instruction execution, and D means it has a JTAG debug port. That means you will be able to debug the hardware, the chip, by connecting it to the JTAG port and your development platform, and you can do a debugging, stop, break, apply breakpoints and other things. Okay, so we will talk about this in the back end of the course. M means it has got a fast multiplier unit, and I means that it has got a in-circuit emulator macro cell, so that you will be able to perform breakpoints and stop the code in between the execution of instructions and look at the contents of the registers. So for doing all this, the processor need to support the debugging, online debugging facility. So these are the different modules which are available in the ARM7 TDMI, which we are looking into. But there are other modules which were added later on to support different kinds of features. The last one, S, means that the IP core is synthesizable. That means, if you remember that I mentioned about hard core and CPU core, hard CPU as well as soft CPU. So this is a soft core where we will be able to take the IP and then build it along with the other chips, and you could even change the layout of that particular CPU what you have purchased from ARM. Now, how a particular revision of, these are all the ISA revisions. Okay, that means starting from ARM v1, we are currently talking about ARM7 TDMI, which follows this ARM v4t instruction set architecture. So there are subsequent improvements to that instruction set architecture, and there are different names to that, and they are mapped to the ARM processor cores. So if the ARM 7 TDMA as well as ARM 9P follows this ISA, whereas ARM 9E and ARM 10 follows V5 ISA, and ARM 11 follows V6. So you could see that following this ARM V40, there are both ARM 7 as well as ARM 9 processors. That means here in ARM 9 there is a 5-stage pipeline, which we talked about that in the last class. So the ARM 9P has a 5-stage pipeline following the same architecture, ISA instruction set architecture of 7 TDMA. So what does it mean? The same instruction set goes through the 5-stage pipeline. So this will ring you a bell that I mentioned in the last class, that when a particular instruction while executing it is accessing the R15 from the register file, it is expected to get a current instruction which is getting executed, that address plus 8, because that is what is being followed by 7. So ARM 9 also simulates that. So in the 5-stage pipeline it would be plus 4. So that difference, I said that ARM 9 is emulating the behavior of ARM 7. It is for this purpose, because both of them are following the same instruction set architecture, and when you are porting an assembly program or a compile program from which was meant for 7 TDMA to ARM 9, it should also run without any problem. So to do that, they introduced this emulation of ARM 7 in ARM 9 core. Okay, so these are the different CPU cores along with their features. Now we will not go into the details of each one of them, but just to highlight few of them. See, this has no cache inside the chip. There is no MMU, or MMU is memory management unit and it is memory protection unit. Though we will be touching upon these features in the later sessions. ARM 7 TDMA as such doesn't have these hardware blocks built into the SoC. So this follows V40 ESA, and it has got a thumb mode. Now if you see the later versions, the ARM P40 is followed by different other CPU also, which has got MMU, but they follow V40 and they have a built-in cache also. So following the same instruction set architecture, they add more hardware modules in terms of memory management unit or a cache, and they build a SoC using this ARM core. Okay. So let us see what are the different ARM instruction types. Hello. 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 Someone is talking in the background. Sorry for the interruption. So let us go into the instruction types of ARM. So this is data processing instruction, which this class of instructions manipulate data within the processor register. Okay. So in this particular session we will be talking about more on this kind of instructions. And then data store instruction. As I told you, the data processing instructions work on only registers, and anything to do with memory is there are separate set of class of instructions which help you in transferring data between memory and processor registers. So they are called data load store instructions. And program status register instruction. If you remember, we spoke a lot about current program status register, CPSR. So if for any reason we want to know the contents of CPSR and then manipulate them, in fact to change the mode from one to the other, we need to copy the CPSR value and then change them. So to do that, there are special instructions which will help you to take the copy of the CPSR and then manipulate it and write it back. And software interrupt instruction, this is to call operating system routines, okay, from the user mode. So this will be going to supervisor mode. So that there are some instructions for that, and branch instruction of course to change the flow of control. There are special instructions for them, and if you want to load the constants into the registers, then there are some instructions for that too. We will go into the details of each of them in successive. Now let us see what are data processing instructions. Now once data is there, if you are manipulating data, we have to see what kind of data that we get from the memory. Okay, so again that depends on the way it is stored in the memory. So here if you see a particular data at that address 1010, you see that bit 0 is here and bit 31 is here, and this is the lower address and this is the higher address. Now when the LS byte of the data, 32-bit data, is stored in a lower address, then it is a little endian mode. So what we are showing, the content of the memory here is a little endian mode. Now this is the address, how the address is increasing. Now let us see how different data types are supported by the processor. Basically it supports 6 data types, 2 each for 8-bit, 16-bit and 32-bit data. But if you remember, we said that ARM registers are all 32-bit value, and any operation being done on the 32-bit registers. So then where is the support for this in the ARM? It is only when you want to store or load from the memory. Okay, so any data which is in the memory could be of any of this type, but once they come into the registers, they are extended to 32-bit words. Okay, and internally ARM reads or operates on 32-bit values. So even if 8-bit value is there in the memory, when it comes to the registers, it will be extended to 32-bit value. Now there are 2 ways it could be done based on the type of data which is being read from the memory. Suppose you are reading a 8-bit value from the memory and its MSB is set, that means it's a negative value. Now when it has to be copied into a register, since you are copying a byte from memory, it will go into the LSB of the register, LS byte of the register, and because that byte which you are copying from memory has a MSB bit set, that is bit 7 is set, that is extended to all the higher bits. Okay, 24 bits of the 32-bit will be made 1, so it will become a complete 32-bit signed value. What happens if an unsigned byte is read? It will be extended by zeros, so the byte value will remain the same. So how does the processor know whether it is reading a signed value or unsigned value from the memory? Processor does not know. So only the programmer who has stored the values in the memory knows whether he or she is storing the value. Based on that, they have to use the proper instructions while transferring the byte from memory to register. Based on the instruction, it will the processor will either sign extend it or 0 extend the bit, so that complete 32-bit value is got in the register and it can operate on it. So the data processing instructions that we are seeing all operate on 32-bit values. Only the data transfer, the instructions which help you in accessing the contents of memory, support different types of data types. Now how are they stored? An 8-bit value could be anywhere in the memory. That means it could be in the lower byte address 0 or byte address ending with 1 or 2 or 3. So based on the LSB bit of the address, a particular byte will be picked from the memory and then it will be copied to the LS byte of the register and sign extended or 0 extended based on whether user wants the byte to be a signed value or unsigned value, interprets it as a signed value or unsigned value. Now what happens to half words? Half word can be stored only on 2-byte boundaries. What I mean by 2-byte boundary means the LS byte of the half word here means 16-bit byte. So LS byte of the half word should be on the even addresses. Okay, it can't start from this. These two cannot be combined as a one half word. Half word has to be either this, which is address. Now this is 1003 and 1004 is this address. So the LS byte of half word can start on 1004 or it can start on 1006. That's the even addresses. So that's about half word. Now 32-bit data types need to start on 4-byte boundaries. That means it has to be either on 0, 4 or 8. Now you can see that the word here starts from 8. It can't start from somewhere in the middle and then go to the higher byte. So these 4 bytes cannot form a word. So when the processor is accessing a word 32-bit value from memory, it will always assume that the lowest 2 bits of the addresses are 0. So it will either read from 0 or 4 or 8 or 12. So the LS, the 2 bits of the addresses will not be considered when it is accessing a 32-bit value. So you should know what we mean by word aligned or a 2-byte boundary aligned or a 4-byte boundary aligned. Only the byte values can remain anywhere, and once they are accessed, it will become a 32-bit value inside the processor. So this is all about data types. Now let us see. Now either you have accessed a word or a byte or a half word, it has come into the register, then it has become a 32-bit value. Now how does the data processing instructions operate on them? That is what we are going to see in this lecture. So these instructions manipulate data within registers. So there are different classifications. A simple move instruction. Why move instructions are coming under data processing instructions? Because the move instructions which help in transferring between registers can manipulate the data. Okay, it can manipulate the data using the barrel shifter. So that's why we call moving the contents of one register to other register also as a data processing instruction. Now there could be arithmetic operations like addition, subtraction, and logical operations like AND or exclusive or, comparison instruction which compares two register values and then say whether it is equal or less than or greater than using those conditional flags, and multiply instructions multiply the content of the register. Now if you remember, there are 3 operands that you could mention in a typical instruction: Rn, Rm and Rd. Rn and Rm are 2 operands, and then one of the operations are done and then it is copied into Rd, which is the destination register. So all these values are all internal registers which are called general purpose registers, which is one among 16 registers that you have, which are always 32-bit byte. Now what is the difference between the 2 operands? The Rn operands directly come into ALU, whereas the Rm operand, the second operand, will go to the barrel shifter based on the type of instruction. Okay. Now let us see. Now how the data processing instruction affect or doesn't affect the CPSR. If you are familiar with 8086 instruction set, you know that whenever you perform any arithmetic operation or logical operation, based on the content of the result, the flags are always affected. Whereas in ARM, it is optional. I will explain how it is being made optional. Except for one type of instruction which are compare instructions. If you know, the compare instruction is meant for saying whether a particular values, two values are same or more or less. So that means they have to affect the CPSR, this is current program status register, so that based on the fact that the control flow can be, different control flows can be taken by the instruction. So ARM ISA gives a special consideration for comparison instruction which always updates the flags. Now you may wonder how other instructions are differentiated, or how an user and a programmer could say whether a particular instruction can affect the CPSR or not. This is the way it is done. Suppose add is an instruction which you want to use in the program. A typical way it is written is RD comes first, that is a destination register. This is a convention ARM follows. Okay, different assembly programming of the programs of different processes follow different convention. So you should be very familiar with what is the way ARM interprets the values. When you write like this, the assembler interprets it as R1 and R2 are added and it is copied into R0. Now you know that when two numbers are added, it is going to impact all the flags of the conditional flags of the CPSR register. What are the conditional flags? Carry flag, zero flag, negative flag, or overflow flag. Now, when you write a code saying that add R0, R1, R2, it doesn't change the values of CPSR. Though this addition can do it, but it is disabled when the user has written just an add. But suppose user has said add yes, that means the user wants whatever arithmetic this particular instruction is doing, and if it impacts the CPSR, that should be reflected in the CPSR. See, I'll give an example. Suppose you are adding two zero values. Suppose R1 is having 0 and R2 is having 0. If you add these two numbers, what you get? You get a value 0 in R0. Now, when the result is a 0, which flag should be set? Naturally, 0 flag should be set. But if S is not there in the instruction, add S was not mentioned, if it was only this, even though R0 has a 0 contents and it is supposed to affect the 0 flag, this instruction will not change the value. What I mean by that? Suppose prior to this instruction execution, if the 0 flag was set or it was clear, it doesn't get changed because of executing this instruction. So the old values of CPSR remains the same. But if add S is there, this 0 adding two 0 values and resulting a 0 written into R0 reflects the CPSR, is reflected in the CPSR flag. So 0 flag gets set and negative flag, of course it has to be 0 because MSB of this result is 0, and overflow flag, there is no overflow here, there is no carry here, so all of them will be clear. Except for 0 flag, all the flags will be clear. So that will be the state of this after the execution of this instruction. So I hope you understand that when you mention a yes after the instruction opcode, this is a opcode which add. If you mention yes, that means this instruction is allowed to change the values of CPSR. Now, how they are affected? It is not only to do with any arithmetic operation, even logical operations or rotate or move or logical shift or anything can affect the flag. So if all of them will affect the flag only when you have a yes associated with those instructions. So this is the way they affect. These are the flags. They get impacted. They get impacted. Anyway, we will talk about those logical operations in detail, and then we'll see how the different flags are getting impacted because of those instructions getting executed. So this is a very important concept, and this is very unique of ARM instruction set architecture. So I want people to understand this and try out this in the simulator so that you see those flags getting changed. Now there is another concept which I am going to talk about: conditional execution. This is also very unique in ARM. So you have to understand the difference between this and the previous thing what I mentioned. What I mean by conditional execution is every instruction, doesn't matter whether it is a compare or a add or multiply or AND operation, anything. Every instruction format, I told you that instruction in a binary format stored in the memory, and all instructions are of 32-bit byte. So out of this 32-bit value, different bits in those instructions talk about what type of instruction it is, what parameters operand it is taking, where it is supposed to write the results. All those things are there. Let us not bother about those fields now. I am talking about the highest n must be bits of the instruction, the 4 bits. Every instruction is coded with a conditional bits which are 4 bits wide and given here. This is called opcode. Okay. Now, what does it mean? Inside the opcode, these 4 bits mean different things. That means if it is set 0 0, it is a for EQ. EQ is a mnemonic that you will be mentioning in the instruction. I will give you an example so that you will understand it better. Actually, what the EQ means? The 0 flag is set. Now, suppose you have an instruction. Let us take an example of add again, and then you say add EQ. Okay, R0, R1, R2. Let me write it and then show you what does it mean. Suppose if you return an instruction, okay, like this. Instead of just mentioning or add, you said that add EQ, then R0, R1, R2. What does it mean? It will be executed only when the CPSR value that is set. Okay, only when the 0 flag is set or due to some other operation before. Okay, because of that the 0 flag was affected and it is in a set condition, then this instruction will be executed. Now what happens? You have to add EQ R0, R1, R2, but 0 flag is not set at that moment. When this instruction is getting executed, the processor verifies, checks whether the 0 flag or the conditional flag is set or not. If it is not set, this instruction is ignored. That means this addition is not performed. So this is what is called conditional execution. Okay. So now I hope you understand this. So the EQ is one of the examples. It could be any of them. Okay. You could write add NB R0, R1, R2. That means this instruction is sitting there in the program. It will never get executed because it doesn't check any flag. Never, do not. Okay, but what I am saying here is this actually you should never be using this particular option. Assume that you have used any of this. Maybe you have used the LE option, add LE. It will get executed only when this condition is true. Okay, either that is 0 flag is set or n is not equal to b. The negative flag is not equal to overflow flag, they are not same, then this instruction will be executed. Similarly, there are so many ways you could say that a particular instruction has to be executed or not. Now what is this AL? This is about always. When an instruction is coded like this, whatever may be the state of this flag, this instruction will get executed. Now you could write add R0, R1, R2. I am saying R0, R1, R2 for an example. It could be any general purpose register. So when you just say add, it means similar to add A. That means when you write just add, that instruction will get always executed. Or you could even say AF. So when you say add and then instruction is not having any of this mnemonic, the conditional bits in that instruction will be set to 1, 1, and 0. Okay. So I hope you understand that. In the earlier case, we show that yes indicates whether a particular instruction can impact the CPSR or not. Okay, we said every instruction can decide whether I can affect the values of CPSR or not. Along with this, if you say add EQ and S, then what happens is whether this execution itself will be based on the value of the current CPSR value, and then if it is allowed to get executed, then whether it can impact the flags or not. So these two are the different conditions. So for a particular instruction, both can be mentioned. You could say that whether this instruction, if it is executed, can it impact the case of flag, and then you can also say whether an instruction need to be executed based on some condition. So both can be there in single instance. Okay, we'll see some examples so that you understand the difference between these two. So this is all about conditional execution. Let us see two examples which will make the thing clear to you. Though I have not introduced assembly program so far to you, don't bother about too much to understand each of them. I will explain you what it means. Suppose you have a stream of instruction like this. Compare means it compares these two values, the content of R0 with a constant phi which is coming along with the instruction, and then if it is same, I told you that compare instruction will always impact the CPSR. So if it is same, it would have set the 0 flag. Now branch on EQ, I told you EQ means 0 is set. So branch only when 0 flag is set. So if suppose these two values are same, you jump to bypass. Okay, you jump means not you or me, but the process will jump to the bypass. Now what happens if suppose 0 flag is not set? Then these two instructions get executed, and then it comes to this particular instruction. Now how does it map to this? Actually from here we go. So if suppose R0 is not equal to 5, the programmer wants to execute these sentence. Now instructions. So if it is not equal, okay, you will not bypass this. That means you will execute this. So what does it do? These two perform the same job of what is mentioned in this here, and then it comes here. Now this is the way typically any processor would be, the assembly would be written. Now because of this conditional execution support provided by ARM, you could do this with a simple instruction like this. Compare this, because why there is no S here, it doesn't matter, because compare always, whether you put S or not, compare always changes the value of CPSR based on the outcome of this instruction. So if these two values are not same, 0 flag would have been cleared. Now come here, add any. Any means what? Not equal to. Not equal to is, suppose 0 flag is not set, that means it is cleared, then you execute this. Again subtract any, that means you subtract the R1 minus R2 and then assign the value to that back to R1, provided that the 0 flag is clear. So this is the way a program is written using this conditional execution support provided by ARM. So this is what I am explaining here. So what is the advantage of this? If you look at the number of words occupied by these 3 instructions and only 2 instructions here perform the same job, that means your code density is better in this case. And then there is one more inherent advantage of doing it this way, which I will explain to you in the coming slides. So code density is included here, and it also says it's efficient in terms of execution time because of pipeline flow is not disturbed. You have to remember, whenever you see any instruction, at least we are talking about ARM7 so 3-stage pipeline, you should have it in your back of your mind. Now what happens when branch execution is encountered, and assume this was a jump, that means they were not equal and it has to go to the bypass. Now it happens in when does this instruction get executed? In the 3rd stage of the pipeline, which is for execution. Already subsequent instructions have been fetched. Okay, this has been fetched and decoded, and this instruction has been fetched. They are all in the pipeline waiting to be executed. Now it encounters that, oh, this bypass condition is true. Okay, these two values are same. So now the instruction flow should jump to this purpose. That means what? The pipeline has to be flushed, and a fresh instruction fetch has to be initiated, and this new instruction, whatever may be, has to come from the memory after this third cycle, and it will take 2 more cycles to go through the fetch and decode stages, and then this instruction will get executed after 3 cycles. You can see that it will be delayed. This execution of this instruction will be delayed by 2 more cycles if we were not using the conditional execution. Now let us see a scenario here. Now compare. Assume the same thing happens here. Okay. Compare has resulted in they being equal. That means what? These 2 instructions need not be executed because they are not equal. But already these instructions are in the pipeline. So when this compare instruction was executed, this is in the decode stage and this is in the fetch stage. So what will happen is the flow will continue, and these 2 will come to the execute stage, but it need not be executed because this condition is not true. So it will just be a no op. So it will skip through. This will also go through. Now the advantage is that within 2 cycles, the instruction which is there to be executed next will be in the pipeline. So there won't be additional 2 cycles of delay because of the jump. So that's why here we say that the conditional execution is efficient in terms of the execution time also, apart from code density. Code density, you can see that only 3 instructions here, whereas here we have 4 instructions to do the same job. So code density is better here, and execution time is also better because of this particular feature supported by ARM. But there are some limitations or side effects to this, which we will talk about in the subsequent slides. So this is an unusual feature of ARM ISA. Conditional codes are, and this I am summarizing it. So conditional codes, what we talk about are these 4 flags. So most of the data pathing instructions do affect these flags apart from one program plus. So almost all ARM instructions contain a 4-bit conditional field, which I showed you. The first 4 bits of the instruction is always to talk about whether a particular instruction needs to be executed based on the particular combination of flags. If it is 1110, it means execute that flag execute that instruction irrespective of whatever may be the value of conditional flag. Other 14 types of the 14 values of those conditional fields gives you different conditions, which I showed you in the table. So conditional execution is supported in almost all instructions, which improves the throughput. I explained you in the previous slide. So if the condition code flag indicates that the corresponding condition is true, then that instruction starts executing. Otherwise, so what has happened is when that instruction comes to the execution stage, it will check the code flag, and if it is matches with the condition, then it will execute normally. Okay. Otherwise, it will be a no op. No op means it is just skipped, so nothing happens. One cycle gets wasted, but no changes to the CPSR or any other register content of the processor. Now, what are the equality conditions? As per the table, it could be equal or non-equal or less than, greater than, signed or signed values. Okay, and accordingly, a particular condition will be checked. So, one more, if you look at in detail, the alternate conditional flags they give you the alternate conditions. One is that is clear, EQ is that is clear, set, and not equal to is that is clear. So like that, every flag is alternating. The conditions are alternating between the codes. That's the way they have ordered it. Okay, there's nothing special about it. Just an information for you. Okay, now what are the benefits of execution? I mentioned it to you. It's better than using conditional branches, because conditional branches take the control of execution to a different instruction by changing the value of PC and disturbing the execution pipeline, and it needs to fetch at least minimum 2 instructions which are in the pipeline. And why 2 instructions? Because I am talking about ARM7, which is 3-stage pipeline. Okay, so always whenever you talk about instructions, please remember the pipeline. That should be in your back of your mind. so that you understand that when an instruction is executed, it is in the execution stage of the pipeline, and the next two instructions in the memory are already into the pipeline. One in the decode stage and the other one is in the fetch stage inside the pipeline. Okay, so whenever that particular branch condition is true, then those two instructions which are in the pipeline needs to be flashed, and the new instruction has to be fetched, which will involve more time. And I told you that how having conditional execution improves the performance, because there is no testing of pipeline, and the density is better. Code density is better because this particular condition is encoded within the 4 bits of the instruction itself. Let us take an example. I want you to when you are listening to the lecture, I want you to freeze the lecture and try to understand yourself what is happening here. All of you are aware of C programming convention here, but how is it mapped and what does it mean? Because if you try to understand it yourself, then my explanation will add to that, and in case if you have any misunderstanding, that will get clear. Okay, good. So you have thought about it, and I hope you have understood what is happening, but I will explain you what is happening here. Assume the R5 is mapped to the variable value. This value could be a local variable or a global variable. It should have been in the memory, either in the stack area or a data area. Now, how has it come to R5? Some instructions before it has already copied using a load instruction from this value from memory to a register which happens to be R5. And where does this 100 come from? It has come from the instruction itself, because when the assembler or the compiler, because it has to be a compiler because it's supposed to be a C code. So the C compiler has seen this content, and then it has generated the compare instruction with 100 embedded into it, because there are some restrictions in how big this constant could be and what are the values it could have. So those things let us not bother now, but assume that it has been interpreted and this constant is here in the instruction. Now what does it do? It compares the value with the 100. If it happens to be equal, 0 flag would have been set. If it is not, this compare instruction would have made the 0 flag to be clear. Now will this impact R5 content? No. Compare instruction does just a subtraction of this value with either immediate or another registered value, and then only takes the result of that and impacts the CPSR and doesn't change the value of any of the operands. So R5 value is not impacted. Anyway, you will know more about this subsequent lecture, but just for a continuity sake, I am saying that it by executing this instruction, it has impacted the CPSR values, conditional flags value, not other values. Now it comes here, add. So add is executed only when 0 flag is set, because we have said add EQ. So it will perform this job. Now what are the R1 and R2? They are supposed to have been mapped to these variables, and it gets added, and then the result is put into R0, which is I. Now suppose 0 flag is not set. Now this will not be executed, it will fall through, but this instruction says it needs to be executed only when they are not equal. That means when the 0 flag is clear, I want this instruction to be executed. So the else part will be executed. So based on the 0 flag set in this instruction, these two instructions, one of them will be executed. Okay, so it is implicit in the instructions which are generated by the compiler. Now let me ask you another question here. Suppose if I put a yes here, is it correct? Suppose if I put yes, what does it mean? We want this instruction to be executed when EQ, when the 0 flag is already set, I want this to be executed, but I want this instruction also to impact the values of CPSR. Now what happens? It will override the value which was there because of this instruction. It may change the 0 flag. Now because of that, this may also be executed if this was having an yes here, so which would be different from what was intended by the programmer. So here you have to remember that suppose you are putting a sequence of instructions which are based on some conditions of CPSR, these instructions should not impact the CPSR value. See, execution of this instruction is controlled by the CPSR, and the decision on whether this instruction can impact the CPSR is based on where yes you put here or not. So you have to make sure that they don't impact the CPSR values because they are not intended here in this particular situation. So you should remember that when if you are writing an assembly program, but compiler may not do that job. Okay. Now let us see another example. I again expect you to freeze the lecture and look at what is the code here and what is being generated here. Try to understand what is happening, which will give a better clarity on how to understand this conditional execution of ARM processor. Okay, welcome back. You hope you have already discussed among yourself or with your neighbor what is happening. Now you see this. Now as per the C convention, when this is true, suppose, then only the Boolean and as per the instruction ANSI standard, this will be evaluated. Okay, that is the way the compiler is supposed to generate code for. So if A is equal to B is true, then evaluate this condition. That means you compare C and D, and if this also happens to be true, then increment E. This is what the original C programmer intended to do. Now the compiler has generated this code. Is it doing what the programmer wanted here? See here, compare R0 with R1. It is very obvious that R0 and R1 correspond to A and B. Now you see compare instruction. It means that it is supposed to affect the CPSR. So based on the outcome, it will impact the CPSR. Now if they are same, 0 flag would have been set. Now it will come here. This compare instruction is again one more compare instruction is coming, but it is a conditional execution. That means if the earlier comparison or earlier operation has resulted in 0 flag being same, or sorry, 0 flag being set, then you execute this instruction. That is true, right? If it is resulting in a equal condition, then only the comparison of C and D should be done. So far so good. Now in the previous slide I told you within this conditional execution you should not put any instruction which will impact CPSR. Now we have used CMP here, which is a compare instruction. Whether you put an S here or not, this is going to impact the CPSR. So whatever may be the state of the compare, the CPSR values based on this instruction is going to be overwritten by this compare instruction now. But is it true in this scenario? Is it correct in this scenario? Yes, because you want this condition also to be available for deciding on whether E++ should be done or not. So compare EQ will compare the C and D values and then set the which it may be set the 0 flag or it may clear the 0 flag, and if it happens to be same, then 0 flag would have been set. That will make this add to execute because add EQ is there. So this is executed based on the CPSR contents of this compare instruction. So that is what is integrated in the C program too. So this is the way it is getting executed. So if you understand this, you must be very clear about where to use conditional execution and how to use and what are the precautions need to be taken, because this is a very unique way of using it. Okay, I would say cunning use of conditional execution. So This is what is explained here. Sorry. Now, how the first comparison finds unequal operand, the second is skip. So, if this is, suppose this itself is false, now this will be skipped. Now, what happens when this is skipped? This will also be skipped. So, if suppose A is not equal to B, it will not go into the if condition at all, as per the C programming convention, right? Now, you want to see whether it happens here. Compare, it is not same. So, EQ condition, so this is not executed. So, now 0 flag continues to be clear. So, because of that, even this will not be executed. So, it will go to the following instruction which is below this if instruction. Okay. So, it satisfies both the conditions, whether both being same or only one being same or the first one being wrong. So, everything is taken care of by this particular set of assembly instructions. I hope you understand this sequence. Okay, so some more details about condition execution. So there is a general rule saying that whenever conditional sequence is there, you should have 3 instructions or fewer. Why we say 3 instructions? Because where will you use a conditional execution? Only when you want to avoid using a branch based on the condition. You put the same condition in subsequent instructions to take care of avoiding branch. But if the instruction that you want to put are more than 3, then the benefit of not using the branch is lost. So you could as well use the branch instruction instead of more instructions being put with a conditional execution. Okay, because I told you the execution advantage you get only when there are fewer instructions to be executed within the conditional. So you suppose inside a if you have more instructions in the program, then compiler would not generate the conditional execution, it would generate a branch because you don't get the benefit of the pipeline advantage. Okay. So because typically a branch instruction takes 3 cycles effectively, you don't want conditional execution instructions to be more than 3, and the advantage you get by avoiding branch is lost. So you should go for using the branch instruction rather than going for conditional execution. Okay, when you have to put too many instructions inside the based on particular condition. And one more thing also you should remember, whatever instruction you put inside the condition, they should not have a side effect. Though in the previous example we saw some compare instruction within the conditional execution which was intended, but if suppose you put some instructions which are not intended to affect the CPSR, you may get a different result. So you have to be very careful when you are using the conditional executions in the assembly. But you should understand what happens so that you fully understand how to write an assembly code here. So apart from that, one more point you should remember also that whether to use a conditional execution or not, you can decide based on the dynamic code behavior. What I mean by dynamic code behavior, suppose when you are comparing 2 values, if most of the time they are supposed to be not same or they are supposed to be equal, based on that you can take a decision because you know which part of the control code is going to be executed more often, and then you can try to optimize that part of the code. So these are all the algorithms or optimization techniques the compiler always do based on the different history or based on the programmer's input. But if you are writing assembly code, you need to keep that in mind because you know the way the assembly flow is going to be, and accordingly you can choose whether to use the conditional execution or not. So with this we have come to an end of what we learned from conditional execution and what are the advantages of them. Now let us see how the data processing instructions flow through the data path of the ARM7 code. Now you remember this diagram earlier we have seen. Okay, you should remember the register files have this number of ports because if you have it in your back of the mind, you will be able to appreciate very well what is happening when a particular instruction is getting implemented by the code. So what I mean by these two, you can always read two parameters operands. At the same time, you could write, the processor could write R15 also into the register file. Okay, in the same cycle. Let us see an example. Before that, I want to just give you what is the barrel shifter do. Where does the barrel shifter appear in the original pipeline? It is here. So Rn, the operand that you pass or that you mention in the instruction, when you say add R0, R1, R2, what is Rn? The first operand, that is R1, which is coming on this bus, and R2 will be coming on D bus. So in add instruction R0, R1, R2, when you say R0 will be read from the register bank directly, but R2 will be read through this, and then the R2 can come to the barrel shifter. Now you can mention some barrel shifter operation. What I mean by barrel shifter operation, some arithmetic shift or right or whatever. You could do it on the second operand before that gets added with the first operand. So in a simple R0, R1, R2, the R2 doesn't have any barrel shifter operation associated with that, so it just falls through it. Otherwise, it will be getting modified here and then coming into ALU. All that happening in a single cycle, which I explained to you in the previous lecture. Okay, now what does the barrel shifter do? RM, it takes in, it does a barrel shifting operation if it has to be done based on the instruction, and then it passes on to ALU as two parameters. So both are 32-bit wide. As I told you, all the registers are 32-bit and all the operands are 32-bit wide. And barrel shifter can perform any of the arithmetic operations. And remember that it all happens within the same cycle. So this improves the performance of the ARM processor. Now let us see what are move instructions. Move instruction is basically to move from either between two registers or an immediate value into a register. That means you have one operand which is always the destination register, and other one, okay, we normally call operand as only the operation that is operand 1 and 2. So here in this case it's a single operand instruction because destination is not considered to be an operand. So it has to move in the destination register. Either the value can come from a register or it could be a 32-bit input or a 32-bit value which is coming from the instruction. Okay. Now, what is the difference between move and movement? Move MEN is move not. That means whatever may be the value which is coming, either it could be from register or an immediate value, it will be reverse. That means you will do a bit reverse operation on all the bits and then copy that value. So you will be toggling the bit from the operand and then copying into a destination. That is what this move MEN does. Okay. So these two are the simple move instructions and MEN or instructions. One just directly copies the value into destination. The other one does a toggling of all the bit positions. If it is 0, it makes 1, or 1 it makes 0, and then reverses the bit and then copies them. So this is a single operand instruction as I mentioned to you. The n could be either an operand, n value, what is mentioned, it could be a register or an immediate value. It gets copied, okay, into the RD. Don't worry about this set of logical operations with barrel shifter test. In the next session, I will be going into details of every one of them. So I thought of showing you a few examples. See, suppose before this instruction gets executed, the condition of the values of these registers were assumed they were 5 and 8. Now move R7, R5. That is R5 is moved into R7. Okay, that is equal to R7 equal to R5. Now what is the value of R5? It's 5. So that is moved into R7 here. So that's what happens after this instruction is executed. Now one more example. This this is the way you can mention the barrel shifter operation. That is, this shift, this LSL means logical shift left. It actually means you are moving the bit positions of R5. Okay, it always implies the next register here to this operand. So R5 is content, the 32-bit value content in the R5 is shifted left, and if it is done logical shift means in the MSC part it will be filled with 0, and how many bits it is shifted? 2 positions. So so because of that, what happens is this value gets changed, and you get the idea. Actually, when you are shifting it to left, what happens is the bit positions. I'll give you an example so that you understand what I mean by this. 1 second. Suppose you have 1, 0, 1. Okay, this is the 101. Sorry about the writing, and the rest of the bits are 0. Now you are doing a left shift. That means you are moving in this direction. The bits in the R5. Now what will happen? This bits, this will become 1 0. Again I 1 0 1 0 and 0. Now what happens? This was originally 4. This means you are 4, and then this one is 5. So 4 plus 1. This is 5 value 5 becomes, this is 16 plus 4 20. So effectively the shifted value R5, that is after this 5 is shifted, you will have 20 in it, and that gets written into R7. So you get 20 as R7 here. Okay, so this is the way you can do it. So if you map this with the diagram, you see that the second parameter of when this R5 is coming on the B bus, and then it goes through the barrel shifter, and then I told you that move operation also does some logical operations with the data. So it gets done, and then that value is copied into it. So move also does some processing with the data. One of the operands is operated upon using the barrel shifter. Okay. So now some more examples using this MVN. Assume that R1 was having a 0 value. After MVN, what happens? I told you that the 32-bit value in this operand is all orange. That means all zeros will become 1, and that value gets written into R1. So you will get this value in R1. So who does this toggling of this immediate value? The barrel shifter, because one of the operand can come through the barrel shifter, so it gets changed, and then that value goes into the R1 value. Now another example, suppose if you have MEN with a immediate value 0 1 is getting into R1. This, when it is toggled, the LSB bit will become 0. That's why you get a E here, 1 1 1 0, and then rest of them will be 1. So these instructions, what I showed you was with the immediate value. Okay, immediate means this constant, this value is coming along with the instruction itself. Okay, not from another register. It's only written into this register R1. Okay, now let us see. This is the MEN operation, how the toggling will happen. Okay, let us see. Now, how can you map this instruction with the data flow happening here? Suppose a register to register move was happening. Now, this is one of the register which is moved, has to be moved to another RG. When you say move Rn, RG, a simple example where this Rn comes directly and there is no shift operation on that, so this particular thing will not be happening. So this Rn will directly fall through the ALU and goes into RG. This value is actually read from R. Suppose move R0, R1. Now R1 is written is read from the register file and then it is written into R0 tag. So this all happen in a one execute cycle. Now what is happening on this side? This is the PC, the R15 getting incremented and then the next instruction getting executed. So if you remember the pipeline, when a particular instruction getting executed, there is a parallel accessing of instructions from the memory also is happening. So for that, a new address has to be generated and then put on the data bus, address bus, and then the instruction will come through data bus and get written into the PC, or the address will be written into PC and the instruction will come in and then get decoded by the pipeline. So this is the way register to register transfer happens, and if there is a LNO shift operation or rotate operation is done, then the barrel shifter will come into play and that will go through this and then the data will be written back into a register. So move operation or any the data path activity is always where the operands are always from register, or it could be an immediate value. Suppose if immediate value is coming, it has to come through the instruction pipeline. I will show you that in the next slide. So this is the way instruction gets executed inside the code. Now assume that there is an immediate value coming. What I mean, if you remember the previous example I showed you, move MEN and then you are saying LSL hash 2, some shift operation with the hash 02. That 0x2 is an immediate constant which has come with an instruction. Now how it gets entered into the instruction here? Because if you remember, different stages have instruction pipeline register which pass on the values. So when this move instruction with the constant was fetched, it was along with the instruction that constant also came. So it passed on through the decode stage and it is available and it is required for the execution stage, because that constant has to flow through this barrel shifter to be operating on the operand or that to be written back into the register. So how is it made available? Through the instruction pipeline register, because I told you that control and data information of instructions, when they pass from one pipeline stage to other pipeline, they pass through the pipeline register and they come into the execution stage at the appropriate time when it is required for the instruction execution. So that immediate constant comes through this, which happens to be a 8-bit value which is encoded into the instruction, and it is required for the barrel shifter, and another operand is also taken from the register and then the shift operation is performed on it and then it is moved back into RD register which is mentioned in the register in the instruction. So how these control signals and choosing a particular registers are done, it is based on the decode stage. It generates some control signals which are also coming to the pipeline register and the data part is set up based on the particular type of instruction. Okay, so I hope you understand this. Before we end the session, let us see few examples so that this concept of conditional execution and the yes flag gets into your mind. Here, analyze this. Move yes. Please remember, move also can impact the CPSR values because it is doing some ASR operation and then the value what is written into R1 is the result of this instruction. So suppose if it is moving a 0 content which is stored in R2 is moved into R1 and you mention it as move yes, R1 happens to be all zeros, so 0 flag will be set. So this instruction is supposed to impact the CPSR. So conditional flags will be affected based on this instruction. Okay. Now what is move EQ? This instruction is suppose this instruction follows this instruction and you allow this move instruction to impact the CPSR. So based on that value of 0 flag, this will be executed. If that happens to be 0 flag is set, then it will be executed, otherwise it will not be executed at all. That means what? This move of R2 to R1 will not happen. The R2 value will be the same irrespective of whether moving happens or not. R2 is not impacted, but R1 will remain the same if this was not executed. And this execution depends on what has happened in the previous instruction if the flag was set. So remember, it may not be the impact of the previous instruction. Whichever instruction executed earlier, if there was whatever is the status of the zero flag or the whatever conditional flag, based on that condition this instruction is executed. So if at this moment when this instruction is enters the execution stage, if zero flag was set, this will be executed, otherwise it will be ignored. Now move MEN also can be appended with ME. That means this will be executed only when the zero flag is clear at this moment. Okay. When I say at this moment, when this instruction gets executed in the execution stage of the pipeline, if zero flag happens to be clear, then it will negate the values in R4 and move it into R4. Otherwise, it will not do anything. Now it's an interesting combination. Okay, move SEQ. Spend some time. This combines two things together. That means, forget for a moment yes. Only CEQ. This whole instruction will be executed when zero flag is set at this time. Okay. Now, okay, the decision is taken. Okay, assume that zero flag is set and this instruction has to be executed. Now it has the option. When this instruction is executed, at the end of this instruction execution, whether can it impact the CPSR flags or not. That decision is taken based on this presence of S. Now because S is here, if zero flag was set prior to the execution of this instruction, this will be executed, and based on the outcome of this instruction, the CPSR flag will be set now. So you are combining both here. Okay. So you have a flexibility and freedom to put any combinations to achieve what you want in your code. So this is the beauty of ARM instruction set. And when you start writing code and when you see the behavior of the different CPSR values and the register content, you will start enjoying writing more and more of assembly code. I want you people to try these kind of instructions. Now having learned move and move-n, I want you to use the ARM simulator and try different combinations and understand what happens to the register, because that simulator gives you a clear way of showing which are the registers or CPS are impacted because of a particular execution of instruction. So whenever you see some values in red, that means that because of the execution of the instruction, these values are impacted or changed. So you can understand this whole lot of things by trying out different instructions in the assembly simulator, instruction set simulator what you have. Please try out and enjoy writing assembly. Okay. So with this, we are coming to the end of the session, and we covered these following features: conditional execution and move and MEN in particular. I want you people to try out these instructions and understand it fully, so that when some more complex instructions are introduced, you are already familiar with this and you will be able to understand them better. So spending a lot of time with the simulator is a must, and I tell you, once you start understanding what is happening at the register level and the flags, you will start enjoying writing more and more assembly. And this is a very niche area where you can get into any job where you are expected to write operating system code or any of the embedded applications, and a very efficient assembly code which is working very close to the processor. Assembly instruction execution and writing assembly instructions is a must. So if you are familiar with ARM instruction set and you are able to write a very good assembly program of ARM code, you will be able to understand any other processor and you will be able to write very good assembly code and you will become a successful embedded system. So wish you all the best, and these are the books as usual I refer, and see you in the next class, and after having tried all the instructions which have been taught in this class. I hope you enjoyed the session. See you in the next session. Have a nice day. Bye bye.